Why does infinity challenge physics? From quantum information to the geometry of spacetime. A hidden problem at the heart of the universe. One of the deepest questions in modern physics is not what lies inside a black hole. The real question is, are space and time truly the fundamental building blocks of reality, or do they emerge from something deeper? A growing line of research in theoretical physics suggests that spacetime may not be fundamental at all. Instead, the deepest layer of reality could be built from structures of quantum information rather than matter itself. While this idea may sound radical, it is grounded in serious mathematical physics, from information to geometry. In quantum mechanics, a physical system is defined not only by particles, but also by its quantum state. To compare two quantum states, physicists use a quantity known as relative entropy. Relative entropy asks a simple question: how distinguishable are two quantum states? What makes this remarkable is that relative entropy is not merely an information-theoretic quantity. Under certain conditions, it can be used to generate a geometric structure. In other words, information can become geometry. This connection is closely related to the Bogolyubov-Kubo-Mori (BKM) metric, an important concept in quantum information theory and statistical physics. The result is striking. Differences between quantum states begin to behave like distances within a geometric space. Tomita Takesaki theory, the hidden clockwork. At the center of this story lies one of the deepest structures in mathematical physics, Tomita Takesaki Modular Theory. This theory reveals a hidden notion of time evolution inside mathematical objects known as von Neumann algebras. Normally, we think of time as something imposed from the outside. Modular theory suggests a far more radical possibility. Under certain conditions, time may emerge from the internal structure of a quantum system itself. For this reason, many researchers believe that modular flow could play a fundamental role in the emergence of spacetime. Why does everything suddenly become difficult? In finite-dimensional quantum systems, everything behaves nicely. Mathematical tools work. Derivatives can be calculated. Geometries can be constructed. But the real universe is not finite-dimensional. In quantum field theory, even empty space contains infinitely many degrees of freedom. This is where the problem begins. Physicists are forced to work with some of the most challenging structures in modern mathematics, type 3-un von Neumann algebras. Within these systems, many familiar tools break down. Some operators become unbounded. The standard notion of a trace disappears. Conventional calculation methods fail. And most importantly, when we try to derive geometry from relative entropy, infinities emerge. The front line of quantum gravity. Today, this problem sits at the frontier of theoretical physics. And yet, important clues already exist. For example, the Unruh effect shows that an accelerated observer can perceive empty space as a thermal environment. The Bissognano-Wichmann theorem reveals a deep connection between modular flow and geometric symmetries of spacetime. These results suggest that modular theory is not merely abstract mathematics. However, fundamental questions remain unanswered. How do modular derivation structures behave in infinite-dimensional quantum systems? Is Iraqi relative entropy sufficiently differentiable in these settings? Is the resulting geometry fully compatible with Einstein's principles of relativity? At present, these questions remain open. What scientific progress really means? Popular culture often portrays science as a collection of answers. In reality, progress usually begins with identifying the right question. Researchers working on modular theory, relative entropy, and quantum information geometry are doing exactly that. The goal is not simply to write down another equation. The goal is to understand how space and time themselves emerge. Perhaps the next great breakthrough in physics will not come from discovering a new particle. Perhaps it will come from understanding how information becomes geometry. Sources and further reading: John von Neumann, Mathematical Foundations of Quantum Mechanics. Iraqi, Relative Entropy of States of von Neumann Algebras. Rudolf Haag, Local Quantum Physics, Bissognano and Wichmann, on the Duality Condition for Quantum Fields. William G. Unruh, Notes on Black Hole Evaporation. Petz and Sudar, Geometry of Quantum States. Vlatko Vidral, The Role of Relative Entropy in Quantum Information Theory.